Hello and welcome back to episode 5 of recreating Baldur's Gate 3's camera inside Unreal Engine. Now, in the last episode we managed to get the orthographic camera working, as well as adjusting the camera height based on the landscape. So as you can see, we can fly around here, and the camera will go up the landscape, down the landscape, but it'll always remain at the height, at minimum, the height of the character. As you can see, as the character goes up the hill in the background there, the camera kind of goes with it. Now, in this episode, we're going to focus on polishing up the camera's movement. Now, there's a few things that involves. That involves adjusting the character's speed based on how far away the camera is from the character. We are basically making bounds as far away the camera can get from the character. And we're going to be adjusting the speed based on how zoomed in you are, which is another feature from Baldur's Gate 3. So, let's jump in. First thing we want to do is we want to load up the camera once again, as per usual. And we're going to make a new function called getCameraSpeed from desired direction. Now, why am I calling it that? If you ever play through Baldur's Gate and you get to the extent, or the furthest extent away from the character you can get with the camera, you'll notice that as it reaches that extent, it gradually slows down. But if you try and move the camera forward, as in towards the character, it's going to have the same speed as it usually would, meaning that the bounds don't dictate the speed as much as the direction as you reach those bounds. Now that's a little confusing, but I'll explain that as we go along. Now, because we're not actually setting any values in the function, we're only getting the values based on other values, the first thing we're going to do is make this a pure function. Now, to show you what exactly that means, is if we drag the function in here, right now it's one of these blue nodes, it needs to be hooked up to the execution pin, meaning if we wanted to use this, we'd have to hook it up like so. But we can make it a pure function because we're not setting any values, and it'll make it a green node. Now, it'll look a little weird right now, but you kind of get the sense of what's going on. It's like the getActorForwardVector or getWorldDeltaSeconds. It's just a function that returns something and takes in a value if we so desire. Thing that we want to get is the desired direction. Now, how do we get that? Well, we already have it. We already know what direction the character wants to go. So, in this variable, or in this function, we can add an input pin, which is the input value. And we can hook that up out here, straight there. And what are we returning with the getCameraSpeed? Well, obviously the speed, which is a float. So what we can do on the output is we can return camera speed and make that a float. So now all we got to do is convert this value into this value. What I will do first of all is our movement speed variable that we already have, I'm going to rename slightly. I'm going to rename this default movement speed. So in the general sense, this is going to be the speed at which we kind of base all of their speed off of. So we can compile and save that. And the first thing that we want to do is find out what the desired direction of the player is. And we can do that by taking the input value. And kind of what we're doing here, we already know which direction we're trying to go by multiplying it by the right vector and the forward vector. So we're going to do the same thing in this variable. We can do getActorRightVector and getActorForwardVector. And we need to break the input value to get both the x and y coordinates so we know which one we're multiplying. And I think x was right vector, wasn't it? X is right vector. Cool, yep. And y is the forward vector. So we want to multiply the right vector by the input. And I'll hit Q to straighten those up. And same again. We take that, hook it up with the forward vector this time. Plug that into the y. I'm going to do just another bit of cleanup here. And what we want to do is we want to add these two together. And the reason we're adding it is we want the absolute direction that we're going. And to do so, we just need to find how much of a force we're applying right and how much of a force we're applying forward. Now that, of course, takes into consideration forward, back, left, and right, because left and back are just negative values for right and forward. And what we want to do with that is we want to normalize it. The normalize function just gives us the vector back in a 0 to 1 scale. Basically, it's a directional vector. Straighten that up. And we want to compare that direction to the direction from the camera to the character. So we can get the player character this time and get actor location. And we want to compare that with the camera location. So what we'll do is we will get actor location, and this is automatically referencing self, but if you want it to be any clearer, one thing you can do is just drag out and do self, and it gets a reference to self. That's not necessary, but it's kind of something a nice little feature if you want to keep things clear. And we can take away, I think this is the way we want to do it. I always get confused. It's either we take away the player character's location from the camera, or we take the camera's location away from the character. We'll find out. This might be the wrong way around. And what we want to do here as well is find that direction. So what we do is we normalize it. And here's where the fun maths comes in, because to compare these two directions, what we can do is something called the dot product. We can find the dot product of these two variables. Plug those in. And what this does is it gives you a -1 to 1 float value based on how similar those directions are. So 1 is they are facing exactly the same direction. 0, they are facing perpendicular, and a -1 is the other way entirely. So you're trying to go away from the character. If that makes sense. We don't really care if it's more than perpendicular. So what we want to do is we want to clamp that to, not clamp axis, we want to clamp float. So we only get any values between 0 and 1, and we're going to use that to multiply our actual speed with. But what we want to do is we only want this bit of logic to kick in if we are in a range far enough from the character. So let's try and figure out how we'd get the distance away from the character we are. We can do that quite easily by... There's a few ways you can do this, really. Really, it's quite similar either way. Get actor location and get actor location of the character as well. So get player character and minus each of them and get the length of that vector, so vector length. Now another way you could do that is finding out the distance between these two vectors is you could drag out and do distance vector. And this is exactly the same as minus and getting the vector length. I like to use this way just because I'm used to it, but you can use the distance vector node if that is any clearer for you. It's quite a clear node, so yeah, it's a nice one to use. Now, what we want to do is we want to start comparing this to a distance that we want to start slowing the character down. Not the character, sorry, the camera down. And to do so, we want to dictate two values. We want to dictate how far the maximum distance from the character can be, and we want to dictate the range at which we slow the camera down. And to do so, we're going to make two more variables. We're going to do a float called max distance from character. Make that a float. Compile, and we're going to do another one called the slowdown range. Slowdown range. So this is, of course, as far away as the camera can get, and this is how far away from that maximum distance we start to slow it down progressively. And what we can do is let's set those values first of all. Max distance, let's ballpark it. Let's go 5,000 units away from the character, and we will go, compile first, we'll go maybe 1,000 units is when we start the slowdown. So compile and save that. We can get the maximum distance from the character and the slowdown range. And a node that is very useful is, we've been normalizing vectors so far, but we can normalize a float within a range as well. They're kind of different, and I'll explain exactly what it means. So normalize to range. It basically compares a float to a range minimum and a range maximum, and kind of gives you a percentage value based on how far away that is from the minimum and the maximum. So we can plug the maximum into the range max, and we can, the range minimum, we will do max distance minus the slowdown range. So in this instance, the range minimum is 4,000, and the range maximum is 5,000 based on, that's correct, based on the values we plugged in here. So 5,000 minus 1,000 is 4,000 for the range minimum. And we can plug the vector length of these two into that. So we're basically saying, give us a value between 0 and 1 for how this distance compares to these distances. And again, as with this value, we don't care if it's outside of those ranges. So right now, if the camera was above the character, it would be at 0, meaning that it would be some negative percentage way down the scale, and we don't care about that. So the return value we're going to clamp between, again, wrong one, clamp float, between 0 and 1. Those are the only values we care about. And what we're going to do is we are going to lerp these two values that we have. So we do a lerp based on the distance from the character. So how much we slow down the character by is dependent on how far away from the character we are. And for the A value for this, we just do 1, because if we're outside of those ranges, or if we're below the slowdown range, we want it always to be at the maximum speed, basically. And as we reach the edge, if we're trying to get away from the character, it'll slow us down. But if we're trying to get towards the character, it's going to be closer to 1, meaning we're not really slowing the character down at all. Now that's a little confusing. It's going to be a lot clearer once we get this actually implemented, and I can show you what I mean by this. So, what else do we need? Well, first of all, we want to do what we did on previous things. We want to multiply this value by the default movement speed, as well as the world delta seconds. So drag out world delta seconds. And plug that into camera speed. So if we compile and save this now, go to the event graph, we want to hook this up to where we already had this hooked up. So we can delete get world delta seconds and the movement speed for both of these. We'll delete one of these pins each because we don't need them. And we will plug the get camera speed from desired direction into both of the multiplications for each direction. Compile and save that, and if we drag that over, let's see what happens. So we try and get away. I might increase the speed actually, just so we get a clearer representation. And to do that, I'm going to adjust the default movement speed to, let's say, 800. So we start moving away off full screen. And as we reach that slowdown range, we should start slowing down. Yeah, there we go. So as you can see, in that range, we steadily start getting slower. If we try and go perpendicular, we can kind of get around the character in a circular motion, but if we try and go further away, it slows down to a full stop. However, it doesn't affect the speed if we try and move towards the character. It's nice and quick. So that is awesome. Now, there's one last thing I want to do in the movement speed, and it's quite a small piece of polish, but it's quite nice to have, and it's very easy to do. We can also adjust the speed of the camera based on how zoomed in you are. In Baldur's Gate, generally, if you're at the maximum zoom, i.e. closest to the character, it's a lot slower. It allows for a more fine-tuned movement control to try and allow the player to look around the map and kind of find things a little easier. However, at its most zoomed out, it's a lot faster. It allows you to get around the map quicker because generally when you're as far away as possible, you're trying to get an overview over what's going on. And now, how do we do that? Very easily, inside the get camera movement, or get camera speed, sorry. What we're also going to do is we're going to multiply this by the zoom percent, but not directly the zoom percent. We're going to lerp this again. So the zoom percent is, of course, a 0 to 1 value, meaning that it's going to lerp nicely between A and B. And if lerp is 100% of A when alpha is 0, so if we are zoomed in, or is it zoomed out? I can't remember if zoom percent is zoom percentage in or zoom percentage out. We will try 1 and 2. So if we're zoomed out, we want it to be twice as fast. We'll add a pin to the multiplication and plug that in. Compile and save, and let's give that a quick test. So, we're very fast when we're zoomed in, and normal speed when we're zoomed out. So we got it backwards. Let's reverse that. So A is 2 and B is 1. Compile, save. Let's see how that works now. There we go. Much nicer. Now we can adjust those values. We don't have to be double the speed. That might be a bit excessive. But we've got limits on how far we can get away from the character now, which is quite nice. Yeah, that's awesome. Sweet. So that is episode 5 sorted. We have polished up the movement. Now let's also, in the next episode, polish up the player movement. That's just a slight change that we're going to make, but just to give the player a bit of feedback. Because right now, if you move the player, you don't really have any indication of where he's moving to. So we're just going to add that ring that dictates exactly where the player's moving to. And yeah, I will see you there. We will soon be getting into the materials. Don't worry. I know you're excited to get into that. I'm excited to share it. Yeah. Cool. I'll see you there.